Hi everybody, this lesson is on exponential growth functions. These are equations that will go up with a non-continuous slope. They are constantly multiplied by a growth factor g, and the variable is x. X tells you the number of times in which you multiply by g. Y, the dependent variable, is going to depend upon x, the number of times which this occurs. Also in these equations typically is a base number, a number that you start at when the power of x is 0. When the power of x is 0, anything to the 0 is going to be 1, with the exception of 0, and therefore this is the sort of the starting amount. It's the y-intercept amount, if you will. If you started at 2,000 and you had any growth factor to the 0 power, it would be exactly at 2,000 for the base. G, again, is the number which you are multiplying by constantly. It is related to the percent of change that happens in every increase of x, in every compounding period of x. Every additional time period, it changes by this percent. However, if you recall in percent change equations, you did not multiply by the percent change. For example, if it was a 15% change, and you wanted to know what your answer was, you would not multiply by 0.15 because that would simply give you 15% of the base. You want the whole base, which is 100% of the base, plus 15% of the base. So in terms of decimals, that will be 1.15. You want all the base plus 15% more. You're multiplying by a number that is larger than 1, therefore the value will be increasing every single time by 15%. The amount that it changes every time will be different because after it grows 15%, the new larger amount is going to have the 15% of that larger amount is going to be more than 15% of a smaller amount. And that will continue infinitely forward. And if you divide it by 1.15, it would continue back into the past as well. Right at the y-intercept, that's where x is equal to 0, because x to 0 is 1, so you just have the base right there. So in the case of 20% interest, you would be multiplying by 1.20. In the case of 50% growth, say for example on a bacteria that grows 50%, it would be times 1.50. If it grew 90%, you would multiply by 1.90. If it grew 100%, that would be the 1 plus 100%, so that's going to be 2.0. If you're multiplying by 2.0, you're really talking about 100% growth every time period. So it's important to notice those two different words. Growth rate, that's like the percent of change. Growth factor. The factor means something that is being multiplied. It is G. G is the growth factor. It's not the growth rate. The thing that you multiply, if it's exponential growth, is going to be greater than 1. If you were by accident to repeatedly multiply by 0.15, 15%, that would not be exponential growth because 0.15 is between 0 and 1. It is not greater than 1. And in that case, you would wind up with 15% of the number, and then after that, you get 15% of that. So if you had 100, after 1, and you're multiplying by 0.15, you wind up with 15. And after you got 15, you'd get 15% of 15, I believe it's 2.25, and you would be actually experiencing an 85% loss every single compounding period as opposed to what you're looking for, which is a 15% growth. So the format for the setup will be the same. You put your starting amount for the base, and you're multiplying by 1 plus whatever the rate of the percent of change is, and that will happen to the x power. If you're graphing this, you put in various powers for x, make sure you throw in a few negatives, in which case, as you go backwards in time, the value when x is negative should be less, y should be less than the base, because at that point, for example, if you were multiplying by 1.15, if you did 1.15 to the negative 2, that's what it would have been 2 time periods before the base. So it had grown 15%, had grown 15%, and then it got to the base. So negative 2 means back in time 2 periods from the present. Okay, here's a typical situation. If you had an infection or perhaps some sort of cell that's rapidly growing and dividing quite quickly, if they grew in number from 200 and they increased 60% per day for 2 weeks, how many would there be at the end of the time? So you got to say, what is the base? Well, the base is 200. What is the percent change? Percent change is 60, but written as a decimal will be 0.60. You can't forget about the whole, 100%, which is 1.0. So the 200 will be times 1.60. And be careful, this is 2 weeks, not 2 days, so that'll be 2 times 7, which will give you 14 compounding periods. So 200 times the growth factor of 1.60 to the 14th will give you the total number of cells at the end of that 2-week period. Go ahead and calculate that, see what you get. Okay, so hopefully you were able to get that. One really surprising fact sometimes when you're doing this is how quickly compounding adds up. If you do 1.6 to the 14th, quite amazingly it winds up being 720. 200 times 720 winds up giving you around 144,115 approximately cells. So you can see with a 60% growth rate over time, that would be quite a number of cells in just 2 weeks' time. Population in the United States is another example of compound growth. We're going to see if you can solve this one. There's U.S. population, currently an estimate would be 330 million. And let's say if it grows at 3% per year, and let's do this over a time period of 20 years. So 20 years from now, when you're like 34-ish, how many people will there be in the United States? So go ahead, base times the growth rate to the number of time periods. Please pause now. Okay, hopefully you worked your way through that. The growth rate of 3% does not translate to 0.3, but 0.03. So 0.03 gets added onto 1. 330 million is multiplied by 1.03, which gives you a 3% increase every single time. It happens 20 years in a row. So if you simply did this part of the calculation, it actually becomes 1.806, which means overall it will be an 80% change, almost 81% change from what it is today. If you finish the math, 330 million times 1.806, it comes out to about 596 million. So it's not quite double. That would take up to 660 to double it, but it's quite a large increase with just 3% per year because of the effect of compounding, where the growth gets compounded over time again and again. Okay, so for your homework, you're going to give the three views of two functions, just two functions. One of which is going to start at 20. The second one is going to start at 2, which is 1/10 of 20. The one that starts at 20 is going to have a growth rate of 5%. The one that starts at 2 is going to have a growth rate of 10%. So this is going to be 10% greater growth rate, but this one starts out at 1/10 of where this one starts off. You need to make two tables, not just one, and you need to do all the calculations for -2, which will be back in time 2 periods, -1, back in time 1 period, 0, which in this case will give you only 2, because 1.5 to the 0 is 1s. So right over here you can just write in a 2. And you do it all the way up to 8. You're going to do the exact same thing for the second function. So you're going to have function number 1, function number 2. You're going to solve for all these values from -2 all the way up to 8. Once you're done, check out what your y values are for both of them. Make sure it's going to fit on the graph. Make a graph which only has quadrant 1 and quadrant 2. Because in these examples, with exponential growth, you're never going to have any negative values for y, because you're always dividing and there's always something left. There's always something left, and as you go forward, it's going greater, greater, greater. It'll never be negative out there. So you only need quadrant 1 and quadrant 2. So you'll need 2 tables, 1 graph, both lines on the graph. You should be able to find an intersection point where they become equal, and then start to see the trend that happens after that. So that's it for your homework. Please do a good job. Label all your axes. Have a continuous scale. No scale breaks in the middle, because it'll ruin your ability to analyze what's going on. Okay, good luck. Thank you.